This video is on electric potential and electric potential energy. Question 1. The following problem refers to electric potential energy E sub p. Is it a scalar or a vector? This is also called electrostatic potential energy E sub p. Part A. Define electric potential energy E sub p. Is it a scalar or a vector? Electric potential energy E sub p is the work done to bring a charge from infinity to a point P. Electric potential energy E sub p is a scalar. This is good for us because we don't have to deal with vector components like sine and cosine. So, part B, what is the equation for electric potential E sub p? What are its units? Here is the equation. Electric potential energy is kQq over R. Problem 2. The following problem refers to electric potential. This is also called electrostatic potential. Part A. Define electric potential. Is it a scalar or a vector? The electric potential at a point in an electric field is the work done per unit charge that would have to be done to bring a test charge to that point from some defined position of zero potential, usually infinity. The electric potential V sub E is a scalar. This is good for us because we don't have to deal with vector components. So important, electric potential and electric potential energy are not the same. Compare the definitions, equations, and units. Part B, what is the equation for electric potential? What about the units? It's work per unit charge. So it's joules over coulombs or volts. So a minimum of one object is required to determine the electrostatic potential at a point. Question 3. Determine the electric potential at point P in the figure below. So we have 3 charges and 3 distances from point P. So electric potential is a scalar, so we don't need to do all that vector component stuff. So we're going to use the equation V sub E equals kq over R 3 times. Let's factor out the constant k. So that's what we did, and there's our solution. Question 4. What would be the electrostatic potential of a point P which is both 12 centimeters from a 25 microcoulomb charge and 6 centimeters from a 50 microcoulomb charge? So you see I just added kq over R twice. Question 5. Determine the electrostatic potential at point X. So you see we have to use a little bit of trigonometry to find out the distance from object A to point X. So we're just going to use kq over R twice. Question 6. Determine the electrostatic potential at point X. So it's pretty straightforward what I did here. I just used kq over R twice. Question 7. Draw a graph of electric potential versus distance of a positively charged solid sphere. So if the electric field is 0 inside the sphere, then the electric potential is constant inside the sphere. So that's why we have a constant, and then it goes down as 1 over R. So memorize this, very important. Question 8. The following problem refers to electric field strength E. This is also called electrostatic field strength. Part A. Define electric field strength E. Is it a scalar or a vector? The electric field strength is a measure of the electric field in a specific location. The electric field strength has a charge as a source and attracts other objects with charge. Electric field strength is a vector. Part B. What is the equation and what are the units for electric field strength? Define each variable. So electric field strength is force per unit charge. Part C, where is the electric field strength 0? Where is the electric field strength maximum? So it's 0 at infinity, according to the equation, and it's maximum at the surface of a charged object. Part D, what are the mathematical limits of electric field strength? Can electric field strength be positive, negative, 0? Yeah, it's between minus infinity and positive infinity. Part E, what is the relationship between the electric field strength and electric potential? Well, here you go. Electric field strength is minus the slope of electric potential with respect to R. So this is the gradient. So this equation tells us that the electric field strength is 0 if the electric potential is constant. If you want to find the electric field strength at a certain point, then take the slope of an electric potential versus distance graph at that point. So here we have an electric potential, which is the red curve. If you want to find the electric field strength, just take the slope at that point. So that's the meaning of this equation. Find the slope of electric potential versus distance to give us electric field strength. Question 9. A small sphere contains a charge of 5 times 10 to the minus 6 coulombs. What will be the direction and magnitude of the electric field at point A? So let's put a test charge at point A. That test charge is always positive. If you put a positive test charge at point A, it's going to be pushed to the right from that sphere. What will be the direction and magnitude of the electrostatic force acting on a proton placed at point A? Coulomb's law is kqq over r squared. What will be the electrostatic potential at point A? It's going to be kq over r. What will be the direction and magnitude of the electric field at point B? It's going to be kq over r squared. Part E, what will be the direction and magnitude of the electrostatic force acting on a proton placed at point B? Once again, it's kqq over r squared. Part F, what will be the electrostatic potential at point B? It's going to be kq over r. Part G, what will be the potential difference between points A and B? That's going to be V sub B minus V sub A. Part H, how much work will be required to move a proton from point B to point A? That's Q delta V. Part I, how much work will be required to move a proton from point A to point B? It's going to be minus 1.13 times 10 to the 6 volts. I apologize, this should say joules because it says work. Okay. Units of work is joules. Part J, which point is a higher potential, A or B? It's going to be A because it's closer to the positive charge. Part K, what will be the electrostatic potential at infinity? That's 0 volts. Part L, what will be the potential difference between infinity and point B? We're just going to use the equation kq over r. Part M, how much work will be required to move a proton from infinity to point B? Part N, how much work will be required to bring an electron from infinity to point B? So the potential at infinity is going to be 0. Question 10, an atom of carbon-12 contains 6 protons in its nucleus. Part A, what will be the total charge of the nucleus of a carbon-12 atom? Part B, what would be the strength of the electric field, a distance of 0.5 angstroms from this carbon-12 nucleus? Part C, what would be the electrostatic potential, a distance of 0.5 angstroms from this carbon-12 nucleus? Part D, what will be the electrostatic potential infinitely far from this carbon-12 nucleus? Part E, what will be the potential difference between a 0.5 angstroms from the carbon-12 nucleus and infinity? Part F, how much work will be done in moving an electron from infinity to a 0.5 angstroms from the nucleus of the carbon-12 nucleus? Part G, what will be the potential difference between a 0.5 angstroms from the nucleus of a carbon-12 atom and a 1.5 angstroms from that same nucleus? Part H, how much work will be done in moving an electron from a 0.5 angstroms from the nucleus of a carbon-12 atom to a 1.5 angstroms from the same carbon-12 nucleus? Question 11. Protons in the nucleus of an atom are on average a distance of 3 Fermi apart. Part A, what will be the electrostatic potential 3 Fermi from a proton? There you go. Part B, what will be the electrostatic potential infinitely far away from a proton? Is 0 volts. Part C, what will be the potential difference between a proton infinitely far away from a proton and a 0.3 Fermi from a proton? Same answer as part A. Part D, how much work will be required to move a proton from infinity to a 0.3 Fermi from a second proton? There you go. Suppose that you hold on to one of these protons and allow the other to accelerate to infinity. What will be the velocity of this proton when it is very far away? Work is the change in kinetic energy. So solve for V final. And we know V initial is 0. Question 12. The following problem refers to equipotential surfaces. Part A, what is an equipotential surface? All points on an equipotential surface have the same electric potential. No work is required to move a charge along an equipotential surface. Part B, how much work is done in moving a charge along the same equipotential surface at 0 joules? Part C, how much work is done in moving a charge along a different equipotential surface? State the equation. Here you go. So it's going to be the area under that curve. So it's going to be the green. Part C, what is the relationship between the object's equipotential surfaces and electric field lines? They're perpendicular to each other. Question 14, draw a spherical negative charge and a spherical positive charge, both with equal magnitudes of charge and volume, with electric field lines and equipotential surfaces. So we've got a positive charge and a negative charge. The electric field lines always point from positive to infinity. Sorry. The electric field lines always point from positive charge to negative charge. And they tell you the direction a positive charge moves. And those black circles or loops are equipotential surfaces. And they're always 90 degrees from the electric field lines. Question 15, draw two spherical negative charges, both with equal magnitudes of charge and volume, with electric field lines and equipotential surfaces. So here you go. The electric field lines, which are red, tell us the direction a positively charged object will move. And those closed loops are the equipotential surfaces, which are perpendicular to the electric field lines. Question 16. Draw electric field lines and equipotential surfaces between parallel plates with an equal and opposite charge. For parallel plates, remember the equations. V equals ED. Okay, so here we go. We have a positively charged plate and a negatively charged plate, and between the plates the electric field lines go from positive charge to negative charge, and outside the plates you see it moves up from positive charge all the way down, and then it goes back up to the negative charge. And those light gray lines you see are equipotential surfaces. So here you go. Equipotential surfaces can be compared to a topographical map. Walking on the same line on a topographical map means that the elevation and gravitational potential energy mg delta H is the same. No work is required to move a mass along the line on a topographical map. All points on an equipotential surface have the same electric potential. No work is required to move a charge along an equipotential surface.